Hello viewers, welcome to another video. In this video, we are going to learn what is transformer, where we use transformer, why we use transformer, and what is the working principle of transformer. So let us start by first going to the generating station in which the electricity is produced. The level of electricity at the generating station ranges between 11 kV to 25 kV. This voltage level has to be stepped up in order to transmit over the long distances in order to avoid transmission losses. So what we do, we use the transformer to step up this voltage from 25 kV to 110 kV up to the 1000 kV. So this is the transmission voltage. This transmission voltage is handled in the substation, which is used to step down the voltage to 11 kV or another voltage for the industry, and also to 400 volts or 220 volts for the domestic uses. So you can see here that the transformers are used as a step-up transformer to step up the voltage in the transmission phase, and then it acts as a step-down transformer for the distribution phase. Now let's see what is transformer. Here on the left I have a motor, and on the right I have the transformer. As you can see that motor is rotating, and unlike the motor, the transformer is a static device. The working principle of the transformer is exactly the same as of the motor based on the Faraday law of electromagnetic induction. So why we call this a transformer? This is called transformer because it transforms the electrical power from one voltage level to the another voltage level, or you can say from the primary voltage level to the secondary voltage level. Here in the figure you can see that there are two windings. The one winding, which is the primary winding, is connected to the source, and the secondary winding is connected to the load. For detailed working principle of the transformer, now we'll go to the another part of this video.
One that requires thousands of volts and a phone which requires very tiny amount of voltage, by plugging them both into the same supply, 230 volts main supply. I mean, the voltage is too low to run a microwave, so how does it work? And the voltage is too high for our cell phones, so why don't they blow up? The secret is a transformer. So what's a transformer? A transformer is a device that can either step up, which means increase, or step down, which means decrease, step down an AC voltage. Okay, what does that mean and how does it work? Well, at the core, the transformer is basically just two coils kept close to each other. One which is connected to the supply, an AC supply, is called the primary coil, and the other which is connected to some device which we want to run, we'll call that the secondary coil. And the basic principle is the supply voltage is going to generate an alternating current. So the current will keep fluctuating back and forth, and current passing through a coil will generate a magnetic field. And that magnetic field will also fluctuate because the magnetic field depends solely on the current. And because of that, Mr. Faraday comes and says, changing magnetic flux through a coil, there will be an EMF induced. So an EMF gets induced in the primary. But what's also important to understand is that that same magnetic field will also get linked, because the second coil is kept very close to the first one. It'll also pass through the secondary. And as a result, as the flux changes over here, as the magnetic field changes over there, the flux also changes in the secondary. And again, an induction takes place in the secondary. And because of that, there will be an EMF generated in the secondary, and as a result, there will be a current generated in the secondary. And that's how the bulb starts glowing. In the secondary and primary are not the same. If I divide them, we'll get the relationship between them. We get Vs divided by Vp equals Ns divided by Np. This means that if the number of turns in the secondary is more than the number of turns in the primary, like shown over here, then notice the voltage in the secondary would be higher than the voltage of the primary or the voltage of the supply. And we call this the step up transformer, increasing the voltage. That's what happens in your microwaves. Your microwave oven requires thousands of volts to run. But you might know that our AC mains supplies only to about 230 volts, so roughly around 200 volts, let's say. So if you want to increase the voltage, say by 10 times as an example, then all we have to do is make sure that the number of turns in the secondary is 10 times more than the number of turns in the primary. Step up transformer. On the other hand, if the number of turns in the secondary is smaller than the number of turns in the primary, notice the voltage in the secondary would be smaller than the supply voltage or the voltage in the primary. We get step down a transformer. And that's what you would use if you wanted to charge your mobile phone, because it requires a very tiny voltage. The AC supply gives you a lot, so you step it down appropriately by reducing the number of turns. Okay. Lastly, how do we make sure the flux here and here remains exactly the same? Otherwise, the equation won't work. Well, a way to do that is by introducing a ferromagnetic core. A ferromagnet has the ability to sort of suck in magnetic field lines. And as a result, almost all the field lines from the primary passes through the secondary, making sure the flux through each coil is exactly the same.
Now we will talk about the paths of transformers. So first of all, we have the laminated core, which is made up of sheet of steels stacking together to reduce eddy current and hysteresis losses. The second major part of the transformer is obviously the winding, which is made up of copper or aluminum material. The third is the conservator, which is used to store the additional cooling oil. Nowadays, in a completely sealed transformer, there is no conservator. Similarly, in the sealed transformer, there is no breather, but in the conventional transformers, the breather is used to absorb moisture from the air during expansion or the contraction of the oil. Another part is the Buchholz relay, which is used to protect the winding from overheating by tripping at certain preset temperature. Let us quickly move to different types of transformers. So basically, the transformer has been characterized into three main types based on construction. The transformer is either core type, shell type, or the spiral core transformer. Similarly, based on the windings, it can be a step up transformer, step down transformer, or the isolation transformer, in which there is no voltage level conversion, only require isolation between the primary and the secondary windings. And the last categorization is based on the coolant material, and this is oil filled self-cooling, oil filled water cooling, and also the third type is the modern type, which is the dry type transformer. So what if you have to specify a transformer? So these are the main parameters which is used to specify a transformer. First is the power rating of the transformer, which can be in kVA or the MVA for the large power transformers. The number of phases, it can be one phase, single phase or three phase, then frequency, then the primary winding voltage and the secondary winding voltage, also the number of taps. Here is the connection type which says DYN11. So this is a convention which means that D stands for delta and Y stands for star. So primary is in delta and the secondary winding is in star. And N is for the neutral. As it is written in the capital letter, it means that star point has a neutral. Type of cooling, here oil natural and air natural is the type of cooling. And then the type of tank, it can be a conservator or a seal type. As I've already told you that in the seal type transformer there is no breather and conservator. So I hope you understand the basic concepts of the transformer. So for more interesting videos, stay tuned and don't forget to subscribe our channel. Thank you for watching.